All right, this is our intro video for section 4.1 for Calculus AB, and we are going to be looking at our other fundamental skill in AP Calculus, and that is the antiderivative. So let's talk a little bit about this. The definition here, function f is an antiderivative of f. I want to look at these two notations here. Notice this is capital F, of course this is little f. So often the capital F is used to refer to the antiderivative of lowercase f. So this is true if capital F prime is equal to little f. So in other words, if the derivative of the antiderivative gives us our original function. So in other words, in effect, an antiderivative is the inverse process of the derivative. Probably makes sense based on the term antiderivative. So I got a question for you. Find a function f whose derivative is f prime of x equals 4x cubed. So take a minute, think about it, write it down. Think of a function f whose derivative is 4x cubed. So I'm hoping you came up with something like this. F of x is equal to x to the fourth plus 10. Or maybe x to the fourth minus 32.7. You might say, wow, is it possible to have more than one answer? Like, are these two different answers correct? And the answer is yes. The answer, there is more than one answer to that question. We could list some more out, right? F of x could equal, x to the fourth, x to the fourth, plus 1/2. I mean, there's really an unlimited number of answers to this question. The reason why is because if you did the derivative, so like if you did the derivative of any of these, we did ddx of any of those, please notice that all these numbers added on the end, the 10, the minus 32.7, the 1/2, they're all constant. And so if I do the derivative of a constant, I get 0. And in each case, I had that x to the fourth there, so the derivative of all of those would simply be 4x to the third and plus 0. So what we do for this, if we were going to officially look for an antiderivative, what we would say is the answer is f of x equals x to the fourth plus c, where c stands for some constant, some unknown constant. And in some cases, we're going to have enough information to find what that constant might be, depending on a particular set of circumstances. Other times not. So in those cases, we would just leave this as a plus c. Just some more terminology here. When we're finding an antiderivative, it could also be said that we are finding an indefinite integral. Indefinite integral. Of course, later on we'll look at definite integrals, but for now we're just looking at indefinite integrals. Now let's take a look at the different parts of one of these expressions. The first symbol, this elongated s right here, that is the integral symbol. It's telling us that we need to find the indefinite integral of whatever comes next. The next thing is the expression inside the integral. We call this the integrand. Integrand. And that's the function in there, right? In this case, the integrand is f of x. The dx is known as the differential, and the differential should match the variables of the integrand. And the capital F of x, this is known as the antiderivative. And finally, the plus c is the constant of integration. So this is that plus c that we saw with that previous one. We thought about all those constants. We could just represent them with a plus c. That's what that's standing for. Now let's take a look at a couple, well, not a couple, let's take a look at a lot of basic integration rules. So you can see, obviously, there's two little chunks to this table, so we're just going to look at the this top part, and then we'll look at the bottom part here in a second. So please notice over here on the left, these are all old derivative rules, rules that we've looked at many, many times. All of these are old. The ones on the right are related, but they are integration rules. So the first one, the integral of 0 dx is equal to 0 plus c, also known as just c. The next one, the letter k stands for a constant. And so what this is saying is that the antiderivative of a constant is just equal to that constant times x plus c. So an example of this would be if we had integral of, say, something like 19x, we would end up with 19x plus c. The next one is a very useful rule. This is called the constant multiple rule. Please notice that it's the integral of k f of x dx. Notice what they've done on the right side of the equation, they've simply brought the k out. You're allowed to do that as long as it is a constant multiple. So an example of this would be the antiderivative of 3 x to the 5th. We could rewrite that if we wanted to as 3 times the integral of x to the 5th dx. You can just bring that constant multiple out and do whatever you got to do with the integrand and then multiply it back in the end. This one right here, this next one in line, this is the antiderivative of a sum or a difference, and all the right side is really saying is that you can, and in some cases you really should, go term by term to find the antiderivative. So if you've got the integral of a sum or a difference, just do the sum or difference of all the integral, or of all the antiderivatives located inside there. Okay, and then the last one on this section is the one that is most commonly used. I would say you'll use this more than any other rule, or at least as much as any other rule. This is the power rule for integrals, and hopefully this makes a lot of sense when you compare it to the power rule for derivatives. If we are doing the integral or the antiderivative of x to the n, what we do is we add 1 to the exponent and then we divide by the new exponent. This is exactly the opposite of the derivative power rule. Hopefully it makes sense that that would be the opposite, since the antiderivative is the opposite of the derivative. Now let's take a look at the second set of integration rules. So you can see all of these have to do with the trig functions, and hopefully because you are very good at differentiating trig functions, you should be very good at looking at these particular integrals or antiderivatives. So the first one here, the antiderivative of cosine is sine of x plus c. Hopefully that makes sense. And then the antiderivative of sine would just be negative cosine. Notice that the relationship with the positive and the negative cosine or sine is exactly the opposite of what it would be with the derivative. Again, hopefully that makes sense based on what you've done before. So the antiderivative of secant squared, what I'd expect you to do is remember that the derivative of tangent is secant squared. So if you reverse that and you think about the antiderivative of secant squared, you should end up with tangent. And then these other three rules are in a similar fashion to that one. You want to remember that the derivative of secant is secant of x tangent of x, and so the antiderivative would just reverse that exactly to get that particular rule right there. Okay, so now what we're going to do on this video is we're going to practice these a little bit, and then we'll have plenty to practice in class as well. So feel free at any point with this video to pause the video and try these based on what we talked about. A lot of these you probably can do. Maybe some of them you might struggle with. I hope that you can do them all, but if you need some help, obviously you can watch the video and see how it should be done. So let's take a look at number 1 first. Okay, so with number 1, I see a couple things in play here. First of all, I see the 5 as a constant multiple. So what I'm going to do is I'm going to bring that 5 out, so it would be 5 times the integral of x dx. Now I'm going to look at what's on the inside here. I'm going to look at the integrand and ask myself, all right, which rule should I use? It's maybe not obvious at first, but it is x to the first, isn't it? So this is going to be a power rule for integrals. So the way that works is this: 5 times x to the 1 plus 1 over 1 plus 1. I'm just using that old power rule. And then plus c. So my final answer might look something like this: 5 over 2, 5 halves, x squared plus c. If you have any doubts about these, you certainly could just do the derivative of your answer, and it should match the original integrand. All right, let's take a look now at number 2. Number 2 says to rewrite first. This is very important. Similar to derivatives, if you remember, to do the derivative of a quotient, we had to do the quotient rule. There's a special rule for that. You'll find that with integrals, integrals of fractions or quotients like this are even more complicated. They can get very complicated very quickly. And so when possible, we want to avoid them. And so like in this one, we're going to rewrite first. The way that we would rewrite is we are going to flip the denominator up. That would give me the integral of x to the negative 4th dx. And again, I'd want to look at this form and ask myself, which form is this and which rule applies? Hopefully you can see that it's just a version of x to the n, and so I would use the power rule for integrals. So here's what it would look like: x to the negative 4 plus 1 over negative 4 plus 1, and let's not forget plus c. So for a final answer, if we clean it up a little bit, it might look something like this, maybe negative 1/3 x to the negative 3 plus c. Number 3, we actually want to rewrite this one as well. It's root x for an integrand, so I would suggest that we rewrite this as the integral of x to the 1/2 dx. The reason why we would want to do that is because, once again, changing it like this, or just changing its form, turns this into just a simple power rule for integrals. So here's how this one works. X to the 1/2 plus 1 over 1/2 plus 1, and then don't forget the plus c. So this ends up being x to the 3/2 over 3/2 plus c. The more common way that you'd see this written would be 2/3 x to the 3/2 plus c. The reason why we could do that is if you divide by a fraction, you just do copy dot flop. This, I guess the way I wrote it would be flop dot copy, but you can just multiply by the reciprocal of that fractional denominator. Next, we're going to tackle numbers 4 and 5. So once again, with number 4, I've got a constant multiple, so this 2 can just come on out. So it's going to be 2 times the integral of sine of x dx. Okay, so as I work on this one, I'm going to have to use a different rule. This is no longer a power rule because it's not x to the n, right, like the other ones we've done. This is just the integral of sine of x. And so you'd want to rely on the idea that you maybe have looked at the rules and you remember that the integral of sine of x is negative cosine. So our final answer here would be negative 2 cosine of x plus c. All right, number 5, you could look at number 5 as a constant multiple, but I would remind you that we did look at a rule that looks like this, the integral of k dx. And that's really what this is right here, the k being a 5. And so this is equal to kx plus c, and so I would say that for this particular integral we would get 5x plus c. All right, we're going to do our final 3 here, 6, 7, and 8. And once again, I encourage you with all of these, if you feel like you can do it, to pause the video and try them on your own and then play the video to see what happens. So take a look at number 6. Number 6, once again, is a fraction, and fractional integrand is going to be difficult at times, maybe even it might feel impossible at times. So if we can avoid them, we will. Here's a way to do number 6. I would flip the denominator up. So it would be x to the 7th minus 6x to the 5th plus x squared times x to the negative 2 dx. And then what I would do is I would distribute that x to the negative 2. And as I distribute the x to the negative 2, let's remember that we need to add the exponents. So this would give me x to the 5th minus 6x to the 3rd, and then it would be x to the 0, wouldn't it? So it would just be plus 1 and then dx. Okay, so then this is just 3 power rules. So this would end up being 1/6 x to the 6 minus 6/4 x to the 4th plus x dx. So I'm starting to move through the, no dx there. I'm starting to move through the rules a little quicker. There's a plus c on the end of that. I hope that's okay with you. If you have any questions, certainly you can ask when I see you next time in class. Okay, number 7. This one gives us a clear rewrite first. We did rewrite number 6 as well. This one kind of makes an emphasis about this. Once again, we've got a fraction. I'm going to try to flip up. Flipping up is going to be a common strategy. It won't be what we always do, but it is a common strategy. So we rewrite this as x plus 1. I know we struggled with this a little bit this year. If I move that radical up, it becomes x to the negative 1/2, and then dx. And like before, I would distribute. So this would give me, as I add my exponents, give me x to the positive 1/2 plus x to the negative 1/2, and then dx. Why this is so nice, this just gives us 2 power rule for integrals, and it should be good. So it's going to be x to the 3/2 over 3/2 plus x to the 1/2 over 1/2 plus c. Let's remember, we typically see this written with the fractions flipped up, so I think we'd get 2/3 x to the 3/2 plus 2x to the 1/2 plus c. for a final answer. And our final example here is number 8. Number 8 is somewhat unique. I don't know that you would see this a whole lot, but here's what we would do with number 8. Again, I encourage you to mess around with this and try this on your own. If you can't do it, that's fine. Here's what you would actually do. To make this work, what we'd need to do is split the denominator up into what it really is. It's really cosine of x times cosine of x. Then what we would do is we'd split it into two different factors. It would be sine of x over cosine of x times 1 over cosine of x. And then, believe it or not, we do a couple little trig identities to make this work. Do you remember what sine over cosine is? Hopefully you're thinking tangent of x. And 1 over cosine is really just secant of x. And then the last step here would be to recognize that the antiderivative of secant of x times tangent of x is just secant of x and then plus c. You'd have to remember those rules from before to be able to do that. All right, so you can see that there's a lot more examples left. When you get to class, we will work on those together. Hope you learned a lot from this video. I'll see you in class.